Hello and welcome. I'm Yuan Zhe from UC San Diego. Today, we are very excited to share our new ICML paper on improving how we understand and optimize deep neural networks. Researchers are increasingly looking at the eigenspectrum of model weights, basically the distribution of the eigenvalues, to estimate model quality and guide training. This is super useful for tasks like figuring out if a model layer is well trained or not. Based on this, we can assign better layer-specific hyperparameters like learning rate. But there is a potential challenge related to the aspect ratio, which is defined as the ratio between the width and height of a weight matrix. In prior work on the eigenspectrum of weights, the aspect ratio of weight matrices was largely overlooked. That is, matrices with different aspect ratios were analyzed in the same way. We will omit some details here, but in general, weight matrices that deviate significantly from being square, such as those that are very tall or very wide, have a large aspect ratio, which can bias model diagnosis results. This means a well-trained layer might be misdiagnosed as poorly trained simply because the matrix has a very different shape from a square. In other words, it has a very large aspect ratio. This aspect ratio bias can lead to incorrect conclusions in model diagnostics and suboptimal performance. To handle this, we developed FARMS, fixed aspect ratio matrix sampling. Instead of analyzing the whole matrix, FARMS samples multiple smaller, consistently shaped submatrices from it. We then analyze the average eigenspectrum of these uniform submatrices. This simple but effective idea removes the bias caused by varying aspect ratios. We have put our method FARMS to the test across diverse AI domains, and the results are compelling. In large language model tuning, FARMS helps reduce perplexity compared to the state-of-art layer-wise tuning methods. We also test our method in different 7 zero-shot tasks, and our method can consistently help models to achieve better test accuracy across different model size and the choices of sparsities. For image classification with classic convolutional neural network models like ResNet and VGG series, applying our method FARMS led to better test accuracy by enabling more precise layer-wise learning rate adjustments. In those plots, the orange bars represent time balance without the layer selection heuristic, while the red bars represent our methods. We can find that for the previous method, time balance is very important to maintain the training quality by using a layer selection heuristic to exclude layers with a large aspect ratio, while FARMS does not need it. This indicates that our method can indeed more accurately estimate these biased layers. And in the case of scientific machine learning, FARMS also demonstrates its value by helping achieve reduction in related error when fine-tuning foundation models on partial differential equation solving tasks. So what does FARMS achieve? It gives us much more accurate and reliable insight into each layer, eigenspectrum, and actual training quality, regardless of its original matrix dimensions. This leads to more balanced model training and more effective optimization across a variety of machine learning tasks. Thanks for watching our video, and we encourage you to check out our paper for all the details.